Hello, my lovelies. It's Susanne, and today we're going to make sense of this clock. You can try it by yourself first if you want to. Let me know in the comments how far you got. We maybe start at 1 o'clock here. Of course, we already know that the result has to be equal to 1, but can we also prove that? So let's take a look at our first problem. 3 to the power of 3 minus 3. First, we can calculate the exponent here. So we keep our base at 3, and 3 minus 3 just equals 0. So we have 3 to the power of 0, and something to the power of 0 is always equal to 1. So this was our 1 o'clock. We figured it out, and can take a look at 2 o'clock here. We have the 8th root of 256. This would be easy to calculate if we had in our square root something to the power of 8, because then the 8th root and to the power of 8 would cancel each other out, and only this number here would be left as a result. But can we write 256 as something to the power of 8? Or if we can, how? So let's take a look at 256 and let's see which numbers are in here. So I want to write this as something times something. Because this is an even number, we know that the 2 is a factor of this number. So we can write the 256 as 2 times 128. And then we take a look at this number and try to do the same. It is an even number again, so I can write this number as 2 times 64. The same thing with this number. I have my 2 times 2 here already, but this is an even number, so I can write it as 2 times 32. The same thing with the 32. It's an even number. I can write it as 2 times 16. Same thing with the 16. It's 2 times 8. Still an even number. So the 2 is in here as well as 2 times 4. And finally, 4 is 2 times 2. So we can write this number as 2 to the power of, how often do we have it? 1, 2, 3, 4, 5, 6, 7, 8. Nice. So instead of this number here in our root, we can write it as 2 to the power of 8. This 8 and this 8, they cancel each other out, and only the 2 is left. And this was our 2 o'clock. 3 o'clock, a beautiful integral. The integral from 1 to 2 over 2x dx. How can we solve such an integral? We're going to write some brackets and take our limits 1 and 2 and write them down here. And now we have to find the antiderivative of this function in here. How can we find it? Well, the rule is the following. If you have x to the power of, if we don't see anything here, it's to the power of 1. Then the rule tells us to take this x, but to increase the exponent by 1. So instead of 1, we're going to write a 2. And in front of this, I'm going to write a fraction. In the denominator, I'm going to write down the new exponent, so my 2. And in the numerator, I'm going to write down the number that was in front of my x here. So the 2 from here, I will write it down here. This is my antiderivative. These are my limits. First, we can simplify this a little bit. 2 over 2 just equals 1. So I have 1 times x squared here, or just x squared. And then we can insert the limits. You always start with the upper limit and insert it for every x that you have in here. It's just this one x. So if we insert the 2, we have 2 to the power of 2. Then you always write down a minus and then do the same with this limit here. So we insert the 1 into our x. So we have a 1 to the power of 2. And now we only have to calculate this. 2 to the power of 2 equals 4, minus 1 to the power of 2 equals 1, and 4 minus 1 equals 3. And this was 3 o'clock. Perfect. 4 o'clock. Okay, the sine. 2 times the sine of pi over 2 and all of this squared. Maybe we start with the sine of pi over 2 first, which is also the most difficult thing in here. Some of you might have this value in their heads. Some of you might not. But you can always use the unit circle to find these values for sine and cosine. Okay, let's take a look at the unit circle then. We draw the x and y axis here, and the unit circle is a circle of radius 1. So our circle goes through 1 here, negative 1 here, and negative 1 here as well. On the x-axis, we can find the values for cosine, and on the y-axis, we can always find the values for sine. We are interested in sine of this angle, so we look at the y-axis to find our value. We always start at this point here, and then we go around our circle, and that depends on this angle. Pi over 2, which angle is that? A full circle, so 1 times around here is always 2 pi. We are not interested in 2 pi, we are interested in pi over 2. Well, so not a full circle. But what about a half circle? So half of this, 2 pi over 2 would be equal to pi. So pi would be a half circle. No, we are not interested in pi. We are still interested in pi over 2. Okay, so we take half of pi then. So half of a half circle, what is that? It's a quarter circle. So we only go up till here at this point. This is a quarter circle. And at this point, we want to find the value of sine, so we look at the y-axis. Which value do I have at this point on my y-axis? I am at the 1. So 1 is my value. And with this, I have 2 times 1 in my parentheses, which is just equal to 2. Don't forget to square this. 2 squared equals 4 then, and this was my 4 o'clock. 5 o'clock. 25 raised to the power of 1 over 2. There are 2 ways now to solve this. The first way is, maybe you know that instead of raised to the power of 1 over 2, you can always write this as the square root of 25. So instead of raising something to the power of 1 over 2, it's the same to take the square root. And the square root of 25 is just equal to 5. So this would be one way to solve this. But if you don't know that, then you can also write the 25 as a power. So the 25 is equal to 5 squared. And then we also have to raise all of this to the power of 1 over 2. So just write the 25 as 5 squared. And then there is a rule that if we want to get rid of these parentheses, we have to just multiply the exponents. So we take the base, the 5, and then we multiply these two. We take the 2 and multiply it by 1 over 2. Okay, so I have my 5 here, and 2 times 1 over 2, I have 2 times 1, which equals 2, and all of this over 2. 2 over 2 is just equal to 1, so 5 to the power of 1 is just 5, and this is my 5 o'clock. 6 o'clock, 3 exclamation mark. Well, this symbol here is the factorial in mathematics. So this is called 3 factorial. And if you have something like 5 factorial, for example, then the rule is you start at this number, at the 5, and you multiply with the next smaller number, times 4. You multiply with the next smaller number, times 3, with the next smaller, with the next smaller, until you get down to 1. This is the definition of the factorial. So, in our case, this means we start at this number, at 3, and multiply it with the next smaller number, so with the 2, and multiply it with the next smaller, which would be the 1. This is our final number, so now we only have to calculate this. 3 times 2 equals 6, times 1 equals still 6, so this is our 6 o'clock. 7 o'clock. What do we have here? This is not a fraction. This is not a vector, because we wouldn't know what to do with this vector. This is the binomial coefficient. And it's called 7 choose 6. And if we want to calculate this, there is a formula. So in general, if you have n choose k, then this is calculated as a fraction. We take the upper number here, the n, and use n factorial, what we just had. And in the denominator, we have this number, so the k, and also factorial. And this is multiplied by, now we subtract these two numbers, so n minus k, and then also factorial. Okay, let's apply this formula here. We have our n, so the upper number here, the 7, and factorial. Okay, and down here we have this k number, so this number here, the 6, and factorial as well, times, then we have parentheses. In here, we subtract these two numbers, so 7 minus 6, and then don't forget the factorial at the end. Okay, lots of factorials in here. Let's see, what is 7 factorial? We said that it means that you start at the 7 and multiply down, so times 6, times 5, and so on until you get down to 1. What is 6 factorial? Pretty similar to this one. You just start at the 6, so you start at 6 times 5 times 4, and so on down to the 1. And 7 minus 6 factorial, let's calculate the 7 minus 6 first. 7 minus 6 is just 1. So 1 factorial would just be you start at the 1 and multiply down until you get to the 1. So you just stop there immediately. 1 factorial is just equal to 1. So we can replace this then already. We have, instead of 1 factorial, we just have times 1. Okay, we don't need times 1 at all. So we only have 7 factorial over 6 factorial. 7 factorial is this beautiful thing here. 6 factorial is this beautiful thing here. We have a fraction. We are allowed to cancel things out if it's possible. Yes, the 6, the 5, the 4, and so on. So the only thing that is left is the beautiful 7 of our 7 o'clock. Okay, 8 o'clock. What is this? This pi is a product symbol, and our product goes from k equals 0 up to 1. So these are the limits of our product. And this in here is what we multiply. So this whole thing that might look a little frightening is just a product. So something times something times something times and so on. And our limits here tell us where we have to start. First, it tells us start at k equals 0. So let's write k equals 0 down here first. This is our first value for k, and we insert for each k that we can find in here, we're going to insert 0. So we have 2 times 0 plus 2, and don't forget the parentheses around here. This is our first factor for k equals 0. Okay, we inserted 0, then we are done with the first factor. Then we have this times, because this symbol here tells us we have a product at the end. And then we're going to increase this number here by 1. So instead of 0, our next k is going to be equal to 1. And we do the same thing. We insert 1 for each k that we have in here. So we have our parentheses, and this time we have 2 times, instead of the k, we write the 1, and then the plus 2. Then, in theory, our k is going to be increased once more, so our next k would be equal to 2, in theory. Why not here? Because the upper limit is 1. They tell us you start at 0 for your k, and you only go up to 1, not to 2 anymore. So this is not going to happen. You stop with your k when you get to the 1. So this is all we have as a product, and now we only have to calculate it. What do we have in our first parentheses? 2 times 0 equals 0, plus 2 equals 2, times, and what do we have in here? 2 times 1 equals 2, plus 2 equals 4. So in total, we have 8. As a result, what was our 8 o'clock? 9 o'clock. What is this? This here, in here we have a matrix with the entries 10, 1, 1, 1. And these lines tell us find the determinant of this matrix. And to find the determinant of a matrix, and we only have a 2 by 2 matrix, so it's pretty easy to find the determinant, we only have to multiply here these diagonals, so 10 times 1 first, and then to subtract the product of the other diagonal. So we also multiply here 1 times 1 this time, and we have to subtract these two numbers. This is the rule if you always want to find the determinant of a 2 by 2 matrix. Let's calculate this. 10 times 1 equals 10. We subtract 1, and 10 minus 1 equals 9. And this was our 9 o'clock. 10 o'clock, the logarithm. People usually love the logarithm, or not. But if the numbers are nice, it's easy to calculate in your head, actually. So here we have log base 2 of 1024. So we have this number and this number to work with. And we want to find this result here. And to find it, we always take the base, so the 2 in our case, and ask ourselves 2 raised to the power of which number is going to be equal to this number in here, so equal to 1024. 2 to the power of which number is going to be equal to this. And this number, the green one that we have to find, is going to be our result of our logarithm. So either you sometimes work with numbers and know the result probably immediately, or if not, we already had today that 2 to the power of 8 is equal to 256. I think it was the problem where we figured out the 2 o'clock. So this is what we already know, that if we raise the 2 to the power of 8, then we get to this number. But this number is too small. We want to get to this number here, so 2 to the power of 8 is not the result. But what about the next larger number, 2 to the power of 9? How do we get there? Well, we have to multiply this number by the base again, so by 2. Same on the other side then, multiply by 2, so that we get to 512. Still too small. So what about the next one, 2 to the power of 10? Well, we multiply by 2 again, and yeah, we get to 1024, which is our number. So we know that 2 to the power of 10 is equal to this number, and the 10 is our result then of our logarithm. And this was 10 o'clock. 11 o'clock. What do we have here? 1011, and all of this to the base of 2. This tiny 2 tells us that this is a binary number. So we have this number system base 2, not what we are used to base 10, where this number would be 1011. But no, this is base 2, so this number is actually called 1011. And we have to convert this binary number now into our decimal system. How can we do that? Well, you always start at the end of your number and multiply your last digit by 2 raised to the power of 0 first. Then you go to your next digit and multiply again by your base, but this time you increase your exponent by 1, so we have exponent 1. Next digit, you take your base and you increase your exponent again, so we have this time the 2 here. And then the last digit here, we have base 2, increase our exponent so that we get to 3. Now we have to multiply all of this. Before we do that, we can calculate these powers here. So 2 to the power of 0, something to the power of 0 is always equal to 1. 2 to the power of 1 is just equal to 2. 2 squared equals 4. And 2 to the power of 3 equals 8. So actually, we have 1, 2, 4, 8, so the number is always doubled. And now, let's calculate this. 1 times 1 equals 1. 1 times 2 equals 2. 0 times 4 equals 0. And 1 times 8 equals 8. And now we have to add these numbers to get our final results. 8 plus 0 equals 8. 8 plus 2 equals 10. Plus 1 equals 11. And this is our decimal number of this binary number here. It's the 11, and that was 11 o'clock. Our last problem here. This looks actually similar to something that we already had today, but we had a pi in here, and that pi told us I am a product. And this time we have a sigma in here, and this tells us I am a sum. So this is actually something plus something plus something, and so on. But the structure is the same. Here are my limits. I start at 1 and go up to 3. So my index, my I, starts at 1, and my I is also in here, so my I is the thing that changes. But we start at I equals 1, so let's write it down here, and let's insert 1 for I first. 3 times 1 minus 2. So you write down everything else as it is, write it in parentheses, and we're done with our first step. We increase our index by 1, so we go to I equals 2. Now we insert 2 for our I, so we have 3 times 2 minus 2. We increase our I so that we are at I equals 3. We insert 3 for I, so 3 times, instead of the I, we write down a 3 minus the 2. And are we going to I equals 4? No, because the upper limit tells us only go up to 3 and then stop. So we don't go further than this. I erase all of our help here, and now let's calculate this. 3 times 1 equals 3 minus 2 equals 1 plus. 3 times 2 equals 6 minus 2 equals 4 plus. 3 times 3 equals 9 minus 2 equals 7, and we get a result of 12, and this was the 12 o'clock, and we solved all of these problems. If you liked my video, please give it a thumbs up. It helps me a lot. I wish you a wonderful day, and I hope to see you in one of my next videos. Take care.